Welcome to another in the Dassault Systems webinar series on Dymola. I'm Michael Tiller, CEO of Exogeny Inc. I've been working with Modelica since 1999, and I've authored a number of books and papers on its use, primarily in the automotive industry. It's my pleasure to be working with Dassault Systems to create a number of 20-minute webinars that explain why I think the Modelica language and Dymola, the Modelica solution from Dassault Systems, provide such a compelling solution for modeling, simulating, and optimizing complex engineering systems. In this webinar, we'll demonstrate how to build models in Dymola using a step-by-step example. Our step-by-step example will be a series hybrid vehicle model built in Dymola. There are several different types of hybrid electric vehicles. The one we will be focusing on is called a series hybrid. A series hybrid has an internal combustion engine, but it is only used to generate electricity. This means there is no direct connection from the engine to the wheels. Instead, electric motors are used to provide torque to the wheels. For this example, we'll build out a simple model step by step. Once we've created this simple model of our system, we'll show how the model can be improved and refined. In doing so, we'll introduce some of the configuration management features in Modelica and show how these features are integrated into the Dymola development environment. The series hybrid example not only demonstrates how components from different engineering domains, like internal combustion engines and electric motors, can be combined to build a complete multi-domain model of your physical system, it will also demonstrate how Modelica can be used to model the control systems as well. Let's get started building our series hybrid vehicle model. We'll start by adding the internal combustion engine model. Modelica models are typically created by dragging and dropping component models into a schematic diagram. There are a couple of different ways to locate models. In this case, we'll use the search dialog in Dymola to search for the engine model. The search functionality in Dymola lets us control what parts of the model are used to identify matches, and then shows us the icon and description of matching models. Once we find the model we are looking for, we just drag it down into our schematic. But one thing to notice about our engine model is that it has two inputs. The first input is used to specify the normalized throttle position for the engine, and the other, a Boolean signal, is used to specify whether fuel should be injected or not. We'll revisit the topic of how to control this engine later. For now, we'll send constant signals into the engine as a starting point and switch to a closed-loop control strategy later. To finish building the engine portion of our model, let's add a rotational inertia to represent the crankshaft. We'll give the crankshaft a rotational inertia of 0.15 kilogram meters squared. Note how Modelica allows us to seamlessly mix block diagrams used to model control functions with mechanical components. More importantly, notice the difference in the connectors. The block diagram components have arrows on them because these components are modeling how information flows through the system. The mechanical connections, on the other hand, are directionless. This is because these are acausal connectors, the kind we mentioned earlier in this series. Acausal connectors allow us to build models that are flexible. In this case, we've connected the inertia to the engine model, but we have the freedom to connect our inertia to any other rotational component. We don't need to worry about whether that component will be a spring, an engine, or a clutch. Whatever it ends up being, we just drag it down and connect it up. With the engine out of the way, let's start looking at the transmission. In this case, the transmission is simply a pair of motors. One motor will act as the generator and will be connected to the engine. Let's add the generator now. We're going to need several different electrical components, so instead of searching for them, let's open the Modelica standard library, specifically the electrical components library. Then we can quickly find the components we need, pick them up, and drag them out onto our schematic. Now that we've added the generator, we need to add the rest of the electrical system for the transmission. As mentioned before, we'll need another motor. This will be used to drive the vehicle. We also need some way to control that motor. So let's insert a current control block. This component is essentially an actuator controlled from outside the transmission. The input to this component is the requested motor current. The actual value for the requested current will come from our control system. For now, let's simply add a constant value, as we did with the engine, until we get around to dealing with control. Next, we connect the generator and the motor. We also need to add a ground component to our electrical circuit. Our electrical circuit is still missing one important thing. Hybrid electric vehicles need batteries to store energy. There are many ways to model batteries. For now, let's use a simple capacitor model with a large capacitance just to keep things simple. The battery is added in parallel with the motor. This means that electricity generated by the generator can flow either into the battery or into the motor. The motor current actuator determines how much flows one way and how much flows the other. We want the battery to start out charged, so we also need to specify the initial voltage of the capacitor as well. So far, we've added our engine model and the transmission model. The engine has two control inputs. One determines whether fuel is being injected, and the other specifies the throttle position. Our transmission model has one input which allows us to control how much current is going to the motor. Finally, the transmission contains a battery which allows us to store up electrical energy for use later. This is typically done to allow the engine to operate at its most efficient operating point. When large torque demand comes from the driver, the torque is delivered by draining the battery rather than forcing the engine to operate at an inefficient point. The battery is also important because it provides a place to store energy recovered from regenerative braking. We'll talk more about regenerative braking later. What's missing now is the actual vehicle. As usual, we'll start with a simple model for the vehicle. The main effects we need to capture are how torque is translated into a force on the vehicle, the drag forces present on the vehicle, and the overall vehicle inertia. For this model, we are only interested in so-called longitudinal dynamics. In other words, we are only interested in modeling the vehicle moving in a straight line. The first step in modeling the vehicle is to add wheels that transform the torques generated from the transmission into forces that act to move the vehicle forward in a straight line. Note how the wheel model has a rotational connector on one end, indicated by a gray circle, and a translational connector, indicated by a green square, on the other. The green square connector represents the straight line motion we talked about, so this is where we will attach the overall vehicle mass. We'll also add a damper to represent losses that scale up with speed. Real aerodynamic drag scales up differently, so this is really just a placeholder. So far, everything looks good. Let's check the model to make sure we haven't overlooked anything. In this case, all the components we were using came out of vigorously tested libraries, so there shouldn't be any issues. But when you advance to the point where you are developing your own libraries, for example creating a proper aerodynamic drag model, Dymola's checking functionality is very useful in localizing mistakes in components. To simulate this model, we move to the Simulation tab and compile the model. Looking in the Variable browser, we can very easily find the vehicle component. By opening it up and selecting the vehicle velocity, v, we see that our vehicle isn't moving. This is to be expected since we are requesting zero motor current. But remember that we are fueling the engine, so we should expect to see the battery charging. Sure enough, it is. This is because the generator is producing electricity, and since it isn't going into the motors to move the vehicle, it is getting pushed into the battery instead. Within the Simulation tab, we can adjust values of parameters. In this case, let's adjust the commanded current to be something other than 0, and then rerun the simulation. Now, instead of seeing 0 vehicle velocity, we see that the vehicle is accelerating. Dymola keeps a specified number of previous simulation results loaded. This allows us to quickly compare against previous simulations. Let's compare our battery voltage trajectory against the previous simulation, where the vehicle wasn't moving. Sure enough, we see that the battery is now charging more slowly because some of that power that was previously going into the battery is now going into the motor to move the vehicle. To really see how this system performs under real-world conditions, we need to refactor this model to add real control systems. We could, of course, go in and start changing components and reconnecting things, but there are a couple of things we need to watch out for. First, when you start reconnecting things, you run the risk of introducing errors. Also, if we start changing things around, what happens to our previous model? What if we still want the open-loop control version for testing? To address these issues, Modelica includes some excellent features to support configuration management. Furthermore, Dymola's user interface makes it very easy to leverage the power of these features. Our first step is to organize these components by subsystem. To do this, we select the components that are all part of the same subsystem, and we use the split model feature in Dymola to create a new subsystem model. Let's start with the engine control components. We select both of them, and then we tell Dymola to split our current model so that the engine control components are separate. We will call this new model our open loop engine controller model, and we'll call the new component in our system engine controller. After a little bit of cleanup, we are left with the following system, where the engine controller is now a separate subsystem. We do this, in turn, for the engine, transmission, transmission control, and vehicle models. After some purely cosmetic changes, we have the following vehicle model. The result is that we have decomposed our system into subsystems. But we aren't quite done unlocking the potential of the configuration management features in Dymola. In order to fully express the configuration management problem, we need to define interfaces for each of the subsystems. Let's start with the engine controller. For our purposes, the engine control must decide what the throttle position should be and whether to fuel the engine. Our current engine control model reflects this by including two output signals. One is a Boolean signal for the fueling command, and the other is a continuous signal indicating normalized throttle position. The problem is that our current engine control model defines both the interface, which defines the signals that it needs to work with, as well as the implementation, that it uses open loop commands. We'll use Dymola's split model feature again to separate this model into both an implementation and an interface. For reasons that will become clear later, we'll also add one additional input signal to the new interface to supply the engine controller with information about the state of the battery voltage. The result is that we now have an interface which defines what is common among all potential engine control models, and a specific implementation that just uses open loop commands. Now we will go through and follow this same procedure for each subsystem. So our engine model will now be split into an interface and a specific implementation. The interface includes inputs from the engine controller and an output shaft for connection to the transmission. The implementation includes the internal combustion engine model we saw before and a crankshaft. We'll follow this same procedure for the transmission controller, and the vehicle model, adding a few additional sensors along the way. Once we've done all that, let's build a new version of our system model. But this time, we will build the system model using only the interfaces that we have developed. Dragging down each interface and connecting them together, we end up with a model that looks very similar to what we had before, except this time we haven't included any implementation details. This model contains only the interfaces. Note how the subsystems have a slightly different border around them. When the subsystem model appears recessed, that means that the interface is defined, but no implementation has been specified. When the interface appears raised, as we will see shortly, that means that an implementation has been specified. What we have created here is an architecture. It captures the structure of our system, regardless of the specific implementations we choose to use. Once the architecture has been created, we won't need to drag, drop, and connect subsystem models anymore. All that work has been done once and for all. All we need to do is decide which implementations we are interested in. Let's recreate our original model with open loop control. To do this, we need to specify the implementations for each of the subsystems. By selecting a given subsystem and choosing the Change Class menu option, we will be presented with a list of implementations for that subsystem. At the moment, we only have one implementation for each subsystem, although that will change soon. We could directly specify our implementation choices in the architecture model, but our better approach is to leave the architecture model as it is and instead create a variant of our architecture that captures our specific implementation choices. To do this, we simply select the architecture model and extend from the architecture. Doing so creates a new model that extends from the architecture. When we say extends from, what we really mean is that our new model starts where the old model left off. From there, we can make further changes, like specifying the implementation details for the different subsystems. This allows us to easily create many different variants of the same fundamental architecture. All these models can exist at the same time, instead of constantly switching one model back and forth between different configurations. It is worth pointing out that there is no limit to how many times we can extend from a model. For example, we might extend from our architecture to create a baseline configuration of our vehicle where all the implementations are filled in. From there, the engine designers might extend from the baseline model but insert a more detailed engine model while keeping the transmission and vehicle subsystem models the same. Similarly, the transmission designers might do the same with the transmission, while leaving the engine and the vehicle alone. These kinds of configuration management features really help our models stay organized and at the same time support collaborative workflows. Once we've gone through and specified all of our initial implementations, we can again simulate the model. Of course, we'd still have the same uninteresting response because of the open loop elements. But now we're in a position to quickly do something about that. For example, let's create a transmission controller that directs our vehicle to follow a specified speed profile. To do this, we'll create a new transmission controller implementation by once again using the extends from feature. Remember that extends from just means that we use the other model as a starting point. Keep in mind that extends from is not the same as copy and paste. We are not copying the contents of the interface into our implementation. This is important because copying and pasting creates lots of redundant code. By extending, we avoid copying and pasting, which makes maintaining all these models easier. Once we create our new transmission controller model by extending from the appropriate interface, we just need to fill in the implementation details. We do this by dragging in and connecting any component models we need to implement our new controller. Once this is done, we can then return to our original vehicle model. Instead of creating a whole new vehicle model, let's extend from the original open loop vehicle model and simply change our selection of the transmission controller. Again, we select the subsystem we are interested in, the transmission controller in this case, and we select from a collection of existing controllers. Once we've configured our new model, note the Modelica source code. It concisely captures the relationship between different variants of our model. In this case, our current vehicle model extends from the open loop vehicle model, but replaces the transmission controller with a different transmission controller. Now let's do the same thing for our engine controller. Taking the engine controller interface and extending from it to create a new model, we implement a state machine. This state machine decides when to turn the engine on and off. It does this by looking at the battery voltage. When the battery voltage is too low, it turns the engine on to charge the battery. When the battery voltage is too high, it turns the engine off to save fuel. To specify this engine control strategy, we follow the same steps as before. We just select the subsystem we are interested in and switch the implementation from one to another. Note the list of implementation choices. This set of choices isn't determined by the user. Instead, Dymola automatically knows which subsystems implement which interfaces. With these two new controller implementations, let's take the vehicle out for a spin. After we simulate the model, we plot the vehicle speed and compare it to the desired drive cycle profile. Here we see the transmission controller is doing a good job of following the drive cycle speed trace. Now let's look at what is going on with the engine and the battery. Notice how the engine comes on when the battery voltage gets too low and turns off when the battery voltage gets too high. Another important thing to know about the battery is that it is charging and discharging even when the engine is off. The discharging comes when the vehicle accelerates because the motor takes energy from the batteries to increase the vehicle speed. But how is the battery recharging when the engine is off? The answer is regenerative braking. When did we implement regenerative braking? We did it in the transmission control. The PID controller in the transmission controller requests positive torque from the motor when the vehicle needs to accelerate, and it requests negative torque when the vehicle needs to decelerate. Because we are using acausal models, all of our components include balance equations for things like mass, momentum, charge, and so on. In order for these balance equations to work out, the kinetic energy in the vehicle has to go somewhere. The motor turns it back into electricity when negative torque is requested, and the resulting current flows into the battery, charging the battery in the process. The important point here is that we don't need to implement regenerative braking. We implement a mathematical model of each component and then impose conservation equations across all the connections. As a result, we are always assured an accurate accounting. This is important because if model developers had to implement all the consequences of the different modes for each component, it would be very easy to overlook something. With acausal modeling, all of this is taken care of. Using this series hybrid example, we've shown how to build a complete multi-domain system model from scratch. Then, we showed how to organize the model into subsystems and enable the configuration management features in Modelica that promote best practices for model development and collaboration. Finally, we implemented some additional controllers to demonstrate typical kinds of effects seen in a series hybrid. While it's good to know that all of this is possible with Dymola, it is also important to realize that you don't need to start from scratch. This architecture-based approach is very common, and many of the specialized libraries that come with Dymola include not only high-quality component and subsystem models, but also the interfaces and architectures that give you a head start in building models of your system. We hope you've enjoyed this demonstration of Dymola's configuration management features. These features result in greater developer productivity while, at the same time, providing a framework for managing the different model variations needed during the product development process. Thanks again, and be sure to check out the other webinars in this series for more information on Dymola.